Um, Good evening, my name is Ron. The following work has on equal terms been created in cooperation with my partner Thomas.
Hi there.
We want to give you an impression on the capabilities of generative AI in EO, more specifically. Methods of Gen AI are mostly based on either of the following. GANs are famous because of their high-quality image generation and elegant formulation, introducing game-theoretic ideas of two competing networks. VAEs, on the other hand, offer a wide field of application, yet are regarded particularly hard to train and in time lack the generative quality of GANs. Keep in mind the special property of the VAE, as not only does it train a decoder, but natively provides an encoder. Somewhat similar to good old PCA, it can break an input image down into a few dimensions. First, via ESA's third-party missions, we received access to WorldView 2 data of most European agglomerations. The data used is atmospherically corrected, pan-sharpened and sampled to 0.5 meters ground resolution. Through Google Earth Engine, we exported surface reflections Sentinel-2 images of more than 10,000 town and city centers, defined by OpenStreetMap. Temporal averaging for cloud removal was applied to create a meaningful data set of global cities. SRTM elevation extracted on mountain ranges globally to create interesting terrain features is the third data set.
We tackled 3 different datasets with 3 different models. Below you can see the randomly generated model outputs. We started with the easiest problem, only generating a single channel surface model. For this problem we used the progressive growing GAN. Next, on the Sentinel-2 cityscapes data, we trained StyleGAN2, which is the state-of-the-art generative adversarial network. And finally, on the WorldView 2 data, we trained an adversarial latent autoencoder, which is a hybrid of GAN and AE model based on the StyleGAN architecture. Apart from generating random non-existent cities, the ALAE model allows us to reconstruct cities from real images. This can be observed in the figure below. Note that the reconstructions in ALAE are optimized in latent space, meaning that the reconstructions focus on the semantic content, rather than the pixel-perfect matching between real and generated images. Here are examples from around Munich. You can see real images and the matching reconstructions. Down here is the same, but for Barcelona. We can also see some limitations here. The model cannot reconstruct certain features like water surfaces or sports fields. We hypothesize that this is due to the limited exposure to these features in the training data and the inherent mode dropping problem of GANs. This could be fixed by curating the input data and using models less prone to bias. So, what else can we do with this latent space? Since we can continuously map latent space into the image space, we can easily visualize any latent changes. For example, combining latent space of 2 images on different layers. In the figure below, we first extract the latent space from real Barcelona and Munich images, then combine the latent codes and generate the resulting mixed image. By mixing different layers, we can create different semantic outputs. Mixing shallow layers, which is on the image on top to the right, this results in changing the road network. And mixing deeper layers results in changing the urban texture. We can go beyond single image manipulations and find meaningful latent directions that work across all generated images. As an example, here you can see the StyleGAN2 Sentinel-2 generations. We can find meaningful latent directions using PCA as introduced in the GAN space method. Here, we vary principal directions in the generated images and name the visible properties: aridity, coast proximity, ruggedness, and population size. Below are some close-up animations, all generated on a different image.
Now for the next steps. Generative methods are hard to handle all around. Consider the optimization problem. Opposed to improving a hard measure like accuracy, we are faced with a complex measure of what appears realistic. The shown methods offer powerful tools to be trained unsupervisedly and allow retrospective adaptation via selecting input by target variables. We now aim to address the following issues. First, for our next poster presentation, we have a specific use case in mind. We want to connect a standalone causal predictive model as an input to our generative model in order to visualize the predictions. Specifically, we want to visualize the predictions of local population change based on climate migration. Having trained on highly desired worldview data, that's the second, we want to use a model to answer bottlenecks in training data, which are based on low availability, high cost, and class imbalances. Third, most recently, GenAI was proposed as communication tool to illustrate consequences, for example, of climate change. While risk maps resonate on the level of administrations or insurances, the general public might much easier be sensitized via relatable images. For this, it will be necessary to further disentangle the dimensions in Latin space to create even more targeted models. Thank you again very much for attending. Bye.